to be about databases and entity relationship diagrams. And I believe that last year you already had the experience with ERDs.
But from my end, this is my first year.
All right, okay. And I think that some people had a bad experience with ERDs as well.
Yep.
Okay. All right. So, okay, Kenneth, if there's anything that I'm going too fast, all right, let me know. All right. There are some things that the videos I'm going to skip because the videos are on Moodle anyway, so you can watch them. And again, the videos are additional information rather than the important stuff that you need to know. Okay. Right. So data in the computer, as you know, computers can only read zeros and ones, so we store data in the form of binary patterns. It's because computers are digital, the waveforms, right? You either have a current or you don't have a current, so it has to be a 0 and 1 combination, the binary combination. Now we are used to our decimal system where we have numbers from 0 to 9, and then obviously we use 2 digits and then 3 digits, etc., etc. However, computers can't read our decimal system. And we store everything. Whatever we store in a computer is data, even software programs for the computer, that is data. And again, there's the videos that I mentioned that it's on Moodle, why we use binary, and the building blocks of data. So the lowest item of our building blocks, the lowest building block is a bit, which can be either a 0 or a 1. And then we start making collections of these bits, right, patterns of these bits, and the next one up is a byte, 8 bits. Although sometimes we talk about a 4-bit composite, which we call a nibble, half a byte. Now the 8 bits will give us 256 combinations. If you look at a pattern of either 8 zeros, which is a value 0, or 8 ones, which is value 255, then we can represent 256 combinations using 8 bits. And then when we start storing data, we talk about kilobytes, megabytes, gigabytes, terabytes, whatever, petabytes nowadays, because that is then the total capacity of the data that we are holding, how much data we are holding in our databases. Now, data can be of different types. We can have numeric data, which can be either integer or decimal. Integer will be full numbers, whole numbers. With decimal, we talk where we have numbers plus what we call the mantissa behind the decimal point. We can have text data, characters. We can also have, besides the alphabetic data, we can have punctuation data, special characters. We can hold graphical data, images. We can hold video. We can hold sound. And we also hold program instructions. Now, when we look at a combination of ones and zeros, we won't be able to distinguish, to define what the data type is. Right? For us, right, or for the computer, for an application program, a pattern of zeros and ones is just a pattern of zeros and ones. However, if we know what the data type is, we can decode that combination. And even our applications can decode that combination. By looking at a pattern of zeros and ones and knowing the data type, then we can know what that represents and what the value is. So for example, if we have a pattern, a string of 0, 1, 0, 0, 1, 0, 1, 1, that can represent a number of different things. If we know that it is a text, a character, and we are using the ASCII code, then we know that that pattern represents an upper a capital K, uppercase K, because lowercase k will have a different pattern. If we know that it is a number, the value would be 75. If we know that it is a machine code, it's an instruction, part of a program, right? We are debugging a program, for example, then we know that that pattern represents the command add. So this is like, remember when we did data and information? Data on its own is meaningless. Once we give it a context, it becomes information. Here we have the same concept. The string of zeros and ones on their own is meaningless. We don't know what it represents. We don't know what it means. However, if we know what the data type is, then we can arrive at the value of that string of zeros and ones. Now, obviously, computers need to manipulate data. They need to do calculations, for example. They need to store text and change text when that is edited. So when we represent numbers, right, the binary representation of numbers, we use the base 2 for calculations, for additions, subtractions, etc. Now when we represent text, it depends on the coding scheme that we are using. So the most common coding scheme is the ASCII character set, and it uses 8 bits for each character. As I said, I just said with the previous slide, we have 256 different combinations. And here we have the ASCII chart. Right? So we have, because that is preceded by a 0, we have 3 bits there and 4 bits here. And you can pick the intersection of each of these, where we have the 4 bits and 3 bits, and we can identify what the characters are. In fact, I said capital K, right, was that pattern that we saw on the previous slide, and lowercase k has a different value. Now, because we can only represent 256 characters with 8 bits, it gives us a bit of a limitation, because we know that for the English language, we have all the characters there, all the alphabet in the English language that is represented. Plus, we have a number of other signs like the numeric signs, right? The greater than, less than, equals, the punctuation marks. Right? So we have a lot of other characters. However, we can't represent all the characters that we find in the word, even our Maltese character set. It has to be mapped to some of these. But if you look at Chinese hieroglyphics, the Chinese alphabet, the Chinese characters, there is no way that we can fit them all into our ASCII code, in our 256 combinations. So Unicode was invented. Unicode was a superset, or is a superset, of ASCII. And instead of using 8 bits, we use 16 bits for each character. Now, we have doubled the length of the character. However, the number of combinations is exponential. Right? We have 65,536 combinations. So we can represent other languages as well. Now, other data types. We have initially computers were just working on numeric and characters, but then eventually, especially with the advent of the PC, we started seeing that other data types can be represented, can be stored. And we look at sounds and pictures, and they are represented numerically. And the process of creating a digital representation of an image or a sound is called digitization. And it works on the concept that we digitize, we represent every part of a picture or a sound into what we call a picture element, a pixel. And that depends on the density per inch of the image that we need to display. Now, representations are always approximations. And if we have a greater resolution, the denser the grid, we have a better quality picture. Now, as for sounds, they can be digitized by dividing their waveforms. Sounds give an analog waveform. Right? It's not like the digital waveform where we have peaks and troughs that represent zeros and ones. So at sound, we'll have waveforms like what we have in this picture here. And a method of digitizing sounds is to sample, right? There's sampling. We look at the wave and we take frequent samples, right, across that wave, and we turn those analog values into digital. When you look at the video that is on Moodle, this will make it much, much clearer. Now, besides, because with sounds and images, we create huge data files, we need to compress data in order to store it and in order to transmit it. The more we need to transmit when we are transmitting data from one computer to another, the longer it is going to take. And when we digitize images and videos, we create huge files. We create a very large number of bits. As an example there, a black and white 8 by 10 inch picture, if it is digitized at a resolution of 200 dots per inch, it will give us 3,200,000 numbers, right, that will represent the different shades of black. So we need to compress data in order to bring the size of that data down into a manageable amount, a manageable quantity. First of all, for storage, remember that even though the price of storage and storage area networks has gone down relatively, right, if we are going to store large amounts of data, we are going to need much more storage devices. So again, the price, right, or the cost for the organization is going to go up. So we use data compression techniques, right? And these are techniques to code the data by removing redundancies. Right? For example, if you have a lot of the same number, right, within your image, a lot of the same color within your image, then there is going to be redundancy. So we try to remove that redundancy, and that is what compression techniques do. And we compress the data when it is stored or transmitted, and then we decompress it when it is used. A good thing about compression is that if we have to transmit images in their original format without compression, even on websites and things like that, they are going to take a very, very long time to load. So our web pages are going to appear much, much slower. But what happens is that those images are transmitted over the internet in a compressed way, and they are decompressed at the client at the client location. So they are decompressed, and the original picture is built up. However, not always, right? The original picture is built up because there are two different types of data compression, and they are lossy compression and lossless compression. And as the names imply, with lossy compression, we are going to have a slight loss. The picture that is reproduced or the sound that is reproduced will not be 100% exactly as the source. So there is a slight degradation in quality. However, with sound and with images, the degradation is so minute, so little, that it will not be perceived by the human eye or the human ear. Okay, so we have minor degradations in data quality. However, we have drastic reductions in file sizes. And this is important because when we are downloading web graphics, then we are cutting down a lot on the time. It makes video conferencing possible because only parts that change are transmitted. The message can never be recovered exactly as it was before it was compressed. Now, with lossless compression, this is important because with business data and text, we can't afford to have the message that is received different from the message that is transmitted. If you are transmitting a balance sheet, for example, if you are transmitting a profit and loss account, it doesn't make sense that the person who is receiving that data is receiving an inferior quality, different data from what is being transmitted. And with lossless compression, we can shrink programs and documents to half their size. The original message is decoded exactly as it was when it left the source, right? So at the destination side, that message is decoded 100% accurately. Now, how do information systems handle data? This is the traditional data organization, what we call the flat file environment. And when we talk about the traditional data organization, we don't mean paper files. We don't need files in a filing cabinet. But we are not talking about hard copy records here. We are talking about computer records. Remember this, because once in an exam, and asked them what the problems were with traditional data organizations, some people said that if you lose the key to the filing cabinet, you can't get at the records. Or if you have photocopies, over time they are going to fade. Alright, so here we are not talking about hard copy documents, hard copy records. Here we are talking about computer records, the traditional way, right, of storing information. And it is a hierarchical structure. Right? So at the top we have a file. A file is made of a number of records. Let's say that we have a customer file. We have 500 customers, so we are going to have 500 records. Each record is made up of a number of fields. What information do we hold about the customer? We hold his name, title, surname, address, mobile number. So we will have a number of fields for a record. Each field will be made up of a number of bytes, depending on the size of the field. Obviously, if we're going to hold a mobile number, right, we don't need to have a field as large as a field for an email address, for example, because it is much shorter. Okay, so the length of the field, right, will be determined by the analyst or the designer of the system according to the maximum length of the what needs to be input into that field. And each character, we talk about name, for example, we're going to allocate 15 characters for a name. Each character is going to be 1 byte because it is going to be a character on the ASCII code. So it is going to be 8 bits. And the byte is made up of a number of bits. So this is how the file is organized. And we start off, before I said these are the building blocks of our data, because 8 bits will make a byte, a number of bytes will make a field, a number of fields will make a record, and the number of records will give us our file. As an example, if we look at a course file, right, for a university, these are the individual records in that file. So that file will be made up of a number of records. A record is these 3 fields here. So a record will have a student ID, a course ID, and a grade. That record is made up of a number of fields, 3 fields. and the field is made up of a number of characters. So the course ID field is made up of 5 characters. Each character is a byte, and it is made up of a number of bits. So the letter I in ASCII has this pattern 01001001, and each of these then will be a bit. And so this is how we build up our file. In fact, if we look at the file, right, as it is recorded on a computer medium, it will be just a string of zeros and ones, zeros and ones, zeros and ones. And we need to know, right, how long each field is, right, what the start of the record is, what the first field in the record is, and how long it is, then the second field, third field, etc., etc. Now, the traditional file environment gave us a lot of problems. This was the first attempt at storing data in computer systems, so obviously it was a case of, again, learning through experience. And the problems that we had with the traditional file environment was that, first of all, each department had its own application and a number of data files. We get back to that famous phrase, data silos, right, or information silos. Each department, because they were independent of each other as far as computer systems were concerned, because obviously departments had to work together. However, each department had its own applications. Initially, we used to have an application for payroll, and that was payroll, and that was that. Application for accounts, and that was that. Right? And everything was independent. Right? And this example here is from human resources, where they would have a number of different files. Right? So again, if you look at different departments, and each of them had a number of systems, you would see how many files, how many different files there would be proliferated throughout the organization. Now, the main problems were, first of all, data redundancy and inconsistency. Data redundancy. Different departments had different applications, but sometimes using data on the same entities, on similar entities. For example, a customer file. Right? Marketing department would have a customer file because they needed to know what the customer's preferences were, what the customer's main products that he was buying were. Accounts department needed a customer file because if there were customers buying on credit, accounts department needed to know the balance of each customer. What invoices are still unpaid? What is outstanding? Right? What do they need to recoup from each customer? Sometimes if we were building customized products for customers, the production people had a customer file as well. Now, some of that information would be specific to that application. For example, the balance would be specific to the accounting application. The marketing people would probably not need to know what his balance is. The production people, for sure, do not need to know what his balance is. But there would be certain information that will be the same. Customer name, for example, address, contact number. So this gave rise to redundancy, having the same data stored in multiple locations. Now what used to happen? A customer changed his address, the marketing people changed his address on their file, right? But the accounting people and the production people perhaps didn't know that there was a change of address and they retained the old address. So this gave rise to inconsistency. data was updated only in one location, not updated in the other location, so there was inconsistent data. Inconsistency used to arise also by using different formats for the same attribute. For example, a date. Right? If in one system the date is in American format, month, day, year, and in other systems it is in the European format, day, month, year, then there is an inconsistency there. There is a discrepancy there. Right? 5-4, is it 5th of April or 4th of May? So depending on which system you are looking at, the date can change. There was a lack of flexibility. We could deliver pre-programmed reports, but not ad hoc reports. Right? We mentioned this. Did we mention this? Yes, when we were talking about decision support systems and management information systems. With management information systems, we deliver pre-programmed reports because when we analyze the system, we know the requirements already. Management will tell us, look, I need a weekly sales report, I need a monthly sales report. So we can agree on the format of that report and we can pre-program it. However, during the course of operations, during the course of the day, management might need an ad hoc report, a report about something that was never asked for, a comparison of product A in location A, for example, with product B in location B. Now, with the traditional file environment, the users had to go to the technical people for these ad hoc reports. And technical people were normally, the programmers were normally employed on new projects or new systems, sorry, and so couldn't really cater for these ad hoc reports immediately. They either had to stop a project, right, or stop working on a new system in order to develop a program to print an ad hoc report. And so it gave less flexibility to the users because users, unless the IT people were forthcoming with that report, users would not have that information at hand. The third problem was poor security. There was little control or management of data. Nearly anybody could change the values of any field on any file. Right? See, all right, there was security, but security was not that strict and that enforced. With databases nowadays, we have automatic auditing of certain fields. The database administrator will set certain fields to be audited, and that audit cannot be tampered with. It is part of the database management system. But with the traditional file environment, because we didn't have this concept of a management system of our data, there was very poor security. And I remember in the early days when a lot of the systems that I had developed were based on the traditional file environment. And when there was an error, we used to write a very small program and just change the value of a field. Nowadays that is taboo. You can't touch the data. Okay, we used to do it. We were talking before trust in the people, right? And I knew that programmers, if they had to change the value of a particular field, it was because there was a good reason to do it. Right? Normally, obviously, I used to give the go-ahead for them to do it. Right? But it could be that you have someone who tries to do something fraudulent, right? And with the traditional way of storing data, that was quite easy. If you had some technical knowledge, you could do it. Another problem was the lack of data sharing and availability. Our famous information silos. The information did not flow between departments. Each department had its own information. They guarded that information jealously. And for them, that information was accurate Right? In fact, when there were inconsistencies in data, each department used to say, no, my data is the correct data. I always kept it up to date. I remember at Farsons, when we wanted to change at Farsons, when I joined Farsons, we had about 4 different customer files. And when we decided to put them in one file, to put them in one database, and we started meeting these discrepancies, right, all the departments said, no, my data is the right data. And sometimes we had to go to the customer himself to check on that data. Which is your right address, which is your correct email address, which is your correct mobile number, which doesn't really put the company in a good light. Hey, client will tell you, you don't have my data, I've been your customer for 20 years. All right, so with each department having its own data and jealously guarding its data, this data did not flow freely between departments. One department sometimes didn't know what information the other department had. And the final problem there was program data dependence. If we changed the data structures, we had to change the applications. We had to go through the programs that used those data structures, and we had to change them and recompile the programs. Now this is an example of the application and file dependence. So we have application file 1 using file 1, application 2 using file 2, application n using file n. If the structure of this file changes, this application needs to change. Now this application could have 10, 20 programs that use this file. So we have to go through each and every one of those to change them and recompile them. For example, we had to extend the size of a surname. We had a very interesting customer at Multacom. His surname was about 32 characters long. It wasn't a double-barreled surname, it was a quadruple-barreled surname. And obviously, when we used to send him a bill, right, the field size for a surname was about 20 characters. Right? This happened with a database as well, but with a database it is much easier to fix. And he used to complain, right, that he was always receiving these bills with half his name. He was a very finicky customer. Right? I think that when he migrated to Melita, there were cheers of joy, but he was always complaining. Right? And then eventually we had amended the file size. But with the traditional file structures, a change in a field size would necessitate the changes to all of the programs that use that file. Sometimes those changes were minor changes, not such a big problem, but the problems were that sometimes the changes were not that minor. And if you have an application with 40 programs that use a file and you miss out one program, suddenly you have the system when it is running in a live environment that one program will not work and it will create problems. Alright, so this was the application and file dependence that was an issue with the traditional way of storing data. So we needed something to eliminate or at least reduce these problems, mitigate these problems. And we came up with databases. Now, the database approach to data management is intended to reduce at least the problems with traditional files. Now, what is a database? A database is a structured collection of electronically stored related data. It is controlled and accessed through computer software. This is where we see the importance of a database management system, a DBMS. Because that DBMS will sit between the application and the data. So any changes to the data, we don't need to change the application. Right? If it's just a question of file sizes, etc., obviously we need to add a new field, right? And we need to capture that field. Then we need to change the program that does the data capture. Right? But for certain changes in the structure, right, of the database, we don't need to go back to the application itself. Now the structure is set by predefined relationships between predefined types of data items. What are the data items that we need to model in our system? How do they relate to each other? And that is the concept of databases. And another thing is that rather than storing data in multiple files, we store data so as it appears to users as being stored only in one location. In actual fact, data is still stored in different, now we call them tables rather than files, but those tables are grouped together and the database itself is visibly one file. As I said, the database management system is a set of programs that are used to define, update, and control access to databases. And the DBMS will be the interface between the application and the physical data files. Now, what are the objectives of a database system? First of all, to eliminate redundancy. We store each data item only once. If we have a customer record or a customer entity, we store customer details in one place. If he changes his address, you don't have to remember that there are 4 different files with the customer address and you have to change them all. There are 4 different applications that use customer address, and so we need to change the address on 4 sets of files. Each data item is available to all authorized users. We no longer have the jealously guarded information by departments. We no longer have departments claiming that data is mine, that information is mine, because I have collected that information, I am updating it, I'm not going to share it with anyone else. Information belongs to the organization. There is no single department that has a jurisdiction over any data item. That data has to be available to all authorized users. Obviously, they need to be authorized users. We can't have data available to everybody. But if you are authorized to view that data, to amend that data, then that data has to be available to you. Another objective is to have an integrated view. Conventional files have data spread over more than one file. With a database, everything is in our database file. We have data independence. We do not need to change our applications every time a data structure changes, because the database management system is going to take care of that. We have better security. With databases, we can set fields, attributes in a database to be audited. If we have sensitive information, we can set that sensitive information for audit. And as I said, the audit files of a good database are tamper-proof. Because if you have someone who changes data and then changes the audit file, then we're back to square one. Alright, so if I change my salary, for example, and then I go to the audit file and say, no, it's not Joe Bella who changed his salary, but Peter Borch, blaming someone else. Right? So that is going to negate the idea, the objectives of an audit file, because the audit file has to give you the true picture. Who changed what? When? What was the value before the change? What is the value now? Now this slide shows data independence. As we can see, we have our database here, our applications, and our applications do not talk directly to the database, but they go through the database management software. So if a field size is changed on the database, we don't need to change any of these unless some of these applications are a report and the field size on the report, actual report, is not large enough. But in most cases, we don't need to change the applications because the database management software is going to take care of that. Now, we distinguish between logical and physical view of data. The logical, the conceptual view of data is the data model itself, the way that the user or the programmer thinks about the data. A customer, what attributes, what characteristics does a customer have? An order, a product item, an item, a saleable item, what are the characteristics? Now the physical or the internal view of data is how the data is actually organized and structured on the physical storage media. Although visually we see that records follow one another, logically, physically, those records could be stored haphazardly, could be stored all over the place. And it is the database management system that pulls them together and presents them to the user in the logical way. Right? So converting the logical view into the physical view and vice versa is done by the programming language, the database management system, and the operating system. So here we have the end users, the external view, the logical view, and this is the internal, the stored database, the physical view. Now, the database management software solves the problems of the traditional file environments, or at least reduces the problems of traditional file environments. And the advantages are that data is stored once in an integrated and coordinated manner. We don't have different copies of the same data, different versions of the same data. So that data is shared by all the users, the departments, by all the applications. We have improved control of information and security. We can access and availability of information will be increased by the database administrator. Normally when we set a database, we are very stingy. We do not give permissions and rights to everybody. Right? We just give those permissions to a few. And then when people start clamoring, look, I need access to that data, I need to be able to change that data, and management okays it, then we start opening it up to other users. So initially the access and the availability will be a bit restricted. But then the database administrator, obviously on the instructions of management, will start opening up more accesses. Users and programmers can perform ad hoc queries of the data in the database management system itself. Now here, remember ad hoc reports? With the traditional file structures, users did not have any control of their data. They had to go to the technical people for ad hoc reports. With a database environment, with database management systems, users themselves can create reports and can create queries. In some cases, we also allow them to update data. And the database management system uncouples programs and data. So data can stand on its own. And users can access that data and they can write reports. You've heard of SQL, SQL. It's a structured query language that allows users to write their own queries, to write their own ad hoc reports. They don't need to go to the technical people. They can do those ad hoc reports themselves. Now, the disadvantages of databases are, first of all, they require careful design. Because if we do not design our database correctly, we are going to create problems. Right? And those data errors will propagate to other applications. Another disadvantage is that they can be slow and less efficient. If there are a lot, we'll be talking about how tables relate to each other using primary keys and foreign keys. If there are a lot of accesses using foreign keys to find primary keys, right? If the path, right, to complete a picture is a lengthy path, then databases can be slow and less efficient than traditional file structures. But obviously, the advantages of databases outweighs these two disadvantages. Any questions so far?
Not from my end, thank you.
Not really.
Okay.
One question.
Yes, say.
Can I- So, if I can compare, would the BMS, it's like the structure of how the CPU or let's say the databases store the data in segment and the other.
It's a joint. Basically, that is the operating system that will find where the actual data, right, the physical data is stored. The database management system gives us the structure of the data, right? But then, right, finding the actual data on the hard drive, on the disk, on the storage area network, that is the operating system that does it.
Okay.
In conjunction with the DBMS, yes. Because there are certain algorithms on how that data is stored to make the best use of your storage area network.
All right.
Okay, Karen?
Thanks.
Right.
Thanks
So,
a lot.
relational databases. When the concepts of databases started appearing, obviously there were different people working using different ideas. And we saw three types of databases coming to light, right? Three database models. The first one is a hierarchical model where the data is organized as a tree structure. Basically, this is like that file structure that we saw, right? The files, reports, fields, etc. Then we had the network model, which is based on a set construct. And the concept is that a record may be in more than one set. And this is represented here. Right, so we have this member down here. Right, this is the higher top level of the database. Now, this down here can be a member of both that set there and that set there. And now this is the network model, and the network model is very complex and difficult to maintain. In fact, the network, this set, right, where a member may be a member of more than one set, this can't be created with a relational model. But there are other ways of going around with the relational model as we shall see. But the network model is very complex and is very difficult to maintain. Now, the relational model is based on the concept that data and relations between them are organized in tables. We have a number of tables, the tables relate to each other, and each table is a collection of records, and each record in a table contains the same fields. Now here, unfortunately, we are using the terms that are normally associated with traditional files. Instead of records in a database, the proper way to call them is either instances or occurrences. Right? But it's the same, it means the same thing as a record. And if you have 500 customers, you're going to have 500 instances, 500 occurrences. But basically, there are 500 records. And each instance, each occurrence, is made of a number of attributes rather than calling them fields. Attributes, characteristics. Customer name is an attribute. Customer address is an attribute. Now the tables are linked via primary and foreign keys. How do we link tables together? The secondary table will have what we call a foreign key that ties up to the primary key of another table. So relational databases are the predominant database technology in business applications. And these are some examples of relational database management systems. Microsoft Access. I think some of you have used Microsoft Access. It's a fantastic user tool. MS SQL, Oracle, DB2. These are used on large mainframes. And there is also an open source database management software called MySQL. Now, database management system is made up of three main parts. First of all, the data definition language. And this is what we use to create the database tables. If you use Microsoft Access, right, you have the table wizard, right, where you start defining the structure of each table. Now, that is the data definition language. Because for each table, we define the characteristics. A customer table, what are the characteristics? His name, his surname, his address, his mobile number, his balance, the date when he joined the company, the date of his first order, for example. The second component is the data manipulation language. Now, this is used to add, change, delete, and retrieve data in the database. So this is when we get new records. How do we add new records to the database? Right, by using the data manipulation language. And then we have a data dictionary, which is an automated tool that stores and retrieves data elements. We need the data dictionary because normally in a database, the names that we give our attributes, our characteristics, would not be necessarily that easily understood by non-technical people. Because in a database, we try to keep a standard way of naming our characteristics, of naming our attributes. Normally, we start by having 3 or 4 letters that denote the entity itself. Cast underscore name, for example, cast underscore surname. But they may not be that easily understood by non-technical people. So we need a data dictionary that translates these technical terms into more user understandable terms.
Sir, if I may ask a question, sorry for
Hey,
interrupting. So, for example, SQL, which is the language which is used, if I'm not mistaken,
Structured query language, yes. This is the data manipulation language.
that would be the data manipulation language, all right?
Okay.
All right. So that's where it falls into.
Right. Wait. Yeah, I can't remember the exact term, but is it find?
Pardon?
With SQL, the command is it find balance, for example, where customer number equals 2345. So that's the data manipulation language. That is, right, the retrieval of data.
All right, but wouldn't, for example, a wizard be built technically with SQL, for example? Or it doesn't work that way?
Not really, no, because it depends on which wizard you are talking about. You might have a query wizard.
Let's say,
Microsoft Access is a query wizard.
uh,
In fact, in your query wizard, right, you can toggle the views. You can view the SQL instruction itself. You can view the result of your query, and you can view the way that the wizard lets you use it. If you're understanding me.
all right.
With a query at the top, you can change views. And one of the views is you can view the SQL itself. You can view the SQL statement.
Exactly,
and
yes.
how you had written it yourself. All right? It's the way the wizard has interpreted the other columns where you have your search statements, if statements, right, whether it is visible or not, what attributes to pick up from the table, things like that. Okay, so that's the data manipulation language. SQL is a data manipulation language.
All right, understood. Thank you, sir.
So now we're going to talk about the data model. Now, do you remember the three approaches that we have for the design of information systems: decision making, transaction cost, and data model? Now we covered the first two. We covered the decision making model in topic 3, and we covered the transaction cost model last week when we spoke about e-commerce. Now the third approach is the data model. Sometimes we have systems that the main focus is information. Right? And the data model approach is based on this concept. The organization can be viewed as a collection of data flows, processes. So what is the data and the information that is flowing through a system? And so information systems should be designed to improve how data flows through an organization, to make that organization, to make the processes within the organization much more efficient. So here with the data model, we say that information systems should improve the ability of the organization to produce, store, and communicate data. Because it's with this data that is available, the information that we are going to give from this data, that the organization is going to work as far as decision making is concerned, for example, right, and the processes that need to be carried out. So with the data modeling approach, we need to look at how we analyze data and how we model data. And we use model-driven analysis methods. When we analyze information systems, and we describe information systems, we use models as much as possible. Here we are going to talk about models within a structured analysis and design approach to development. Right? More recently, right, you've heard about object orientation, UML. Right? There are other models that are used for analysis and design. But here we are going to see some of the traditional models that are used for analysis. Now, why do we need model-driven analysis? Because when we see pictorial system models, they are much easier for users and even technical people to visualize them. Now, we draw models for with two objectives in mind. The first objective is so that we can discuss these models with the users, so that we can identify whether we have the correct requirements, whether we have understood users correctly, whether we have included all the requirements in our model. And when we use models facing the user, when we use models to discuss with users and ensure that we have the requirements correctly, those models have to be as simple as possible. Right? Because if we put in a lot of detail in them, then it is going to confuse users. The second objective is so that we can pass on those models to the developers themselves. Now, for the second objective, we need to have much more information on those models because obviously the technical people need that information because they need to develop the systems based on that detail. And we use models because, as the English say, a picture is worth 1,000 words. Here, right, we can see a model of a car, right, with all the dimensions, internal, external dimensions of a motor car. If we had to write a document using natural language to explain these dimensions, right, it will be quite a hefty document and it will be very difficult to try to follow and to try to find one particular dimension. Here with a model, it is very easy to, you want to know what the internal, the greatest internal width of the car is, you just home in on one part of that model and you have your answer. And with a natural language description, it might take some doing to find what you want. And it is much easier to refer back here than it is to refer back to a document. Especially if you have a 200, 300 page document and you need to find something in that document, the chances are that you'll read through it 3 or 4 times and you'll miss it anyway. And so we use models. We use model-driven analysis. Now, why do we need to model data? Because if we don't model data, we're not going to get our information. Information is the result of data. We get information from giving data context. We need that information because information is the lifeblood of the organization. Without information, an organization will not work well. So we need to ensure that we have the building blocks for the information that we need to give users. If users want an age debtors report, for example, the invoices that are outstanding, how old are they by customer? We need to know what data we need to maintain in our system to be able to give that report. Otherwise, if we don't have the source data, we don't have the core data, we can't gather that information, we can't assimilate that information. Now we have two approaches for modeling data. And these two approaches are not mutually exclusive. It is not we either use a top-down approach or we use a bottom-up technique. We use both of these approaches. And we start off with a top-down approach, which is entity relationship modeling. We start looking at data groups. At the top part, this is why it's a top-down approach. What are the finished, the final entities that we need to model? How do we break them down into their different attributes? How do we relate them to each other? And this is the first attempt at a data model. That is why we start off with the top-down approach. However, this first attempt does not give us a complete data model. We can't go to a database administrator with our entity relationship diagram and tell him, create a database out of this. Because the database administrator will not be able to do it, or if he does create a database, it's not going to be an efficient database. So we need another technique, and we need what we call a bottom-up technique. So first we do a top-down approach, we do an entity relationship diagram, and then we normalize data. And it's a bottom-up technique because first we look at the smallest individual items. And then there are systematic rules that need to be followed in order to structure the data. Now, once we do normalization, we have the final structure that can be implemented. With the result of normalization, we can go to a database administrator and ask him to create a database. And he will be able to create a database for us. So let's look at the top-down approach first. Entity relationship diagrams, right? ER models. Based on the relational database concept, and again, we consider data as being stored in squared tables, tables that have rows and columns, very similar to Excel. I know people who keep a very rudimentary, very basic customer information file, for example, on Excel. The columns are the different attributes that we keep, the different characteristics that we keep about each customer. The rows are the different customers that we have. As I said, we call rows occurrences or instances rather than records, and we call columns attributes rather than fields. And the entity relationship diagram model consists of three interrelated pieces of information. First of all, the data objects themselves. What do we need to model in our system? What are the data objects? The attributes that describe these data objects. What characteristics do these data objects have? And the third part is the relationship. How are they connected to each other? What data object relates to which data object? So what is a data object? A data object is something that will be manipulated within the system. That we need to hold information, we need to hold data about within our system. For example, if we have a traffic management system, we would need a car data object. The data object will have many instances. We will have many cars in our traffic management system. And each instance of an object is identified uniquely. We need to identify if we have 10,000 instances of a particular data object, we need to identify it uniquely. Each one of them, right, has to be identified on its own. So for example, right, for a car ID, to identify a car, we may use the chassis number. We'll be talking about the types of identifiers that we can use. For the time being, let's say that for the car, we use the chassis number. Each data object plays a necessary role in the system. If we don't record that data object in the system will not work. The system can't function if it doesn't access the instances of that object. Each instance is described by attributes, and these attributes themselves are data items or data object, and attributes are all data items. Now, a data object will contain one or more attributes, and these attributes act as descriptors, right? Characteristics. They give us something about the aspect of that data object. And one or more of the attributes has to be defined as a unique identifier. Now we pick a unique identifier because it has to be, first of all, unique. There is no other value within.
Hello.
Yes.
Yeah. Sorry to interrupt you. Do you mind if I leave this session being recorded and I have to leave because my mother is at hospital and they called me.
I'm very sorry about that. No problem.
Okay, thanks a lot.
I hope that she gets better.
Okay, thanks. I leave it recording.
Okay, Carl. Okay.
Thanks a lot.
Okay. Ciao, Carl.
Bye-bye.
Alright, so these attributes give us a description, will give us something about the data model, the data object, Okay, I was saying that one of them or a number of attributes have to be a unique identifier, and I was talking about the unique identifier having, first of all, to have uniqueness. Secondly, it cannot be a null value. And thirdly, it has to be, as much as possible, static. It doesn't change. Because if a unique identifier changes, we might have problems. Now here we have an example of our data object, which is a car, and these are the attributes of the car. These all describe a particular car. And if we see some examples here, we've got our ID here, which is probably the chassis number, the make, the model, the body, the color, and the owner. Right? And we could have 10,000 instances of this, because we will have 10,000 different cars in our database. Now, the primary key is the attribute that identifies a specific instance. So this specific instance is going to stand out among all the instances within the table. We are referring to this particular car. We have 10,000 cars, but we are talking about a particular car. So we need to identify it uniquely. And we identify it uniquely by the primary key. And as I said, the primary key has to satisfy three main characteristics. Uniqueness must have a value, and the value does not change. And the primary key is the link between one data object and another in a database. Again, there's another video about primary keys that you can view at your leisure. Now, on the next page, right, I'm going to have a sample of a database, and I'd like you to tell me which attribute would make a good primary key. So again, right, we have our example from a car
Registration.
data object. We have a number of instances here. We have 5 instances, and we have a number of attributes. Now, which one of these do you think would be the best primary key? Would give us, right, a good primary key and would satisfy those 3 requirements for a primary key: uniqueness, not being null, and being static.
The car registration number.
Okay, you haven't said car registration number. Do you agree, or do you think that?
We can use two, and we're not going to choose two on this. We have the current number and which is unique for that country, but the chassis number is unique worldwide.
Uh-huh.
Because there is only one car with that chassis number anywhere around the world. Whereas you can have a car registration number, ABC 123 in Malta, and you can have the same one in Poland, for example.
Okay. Now, besides, you're right, Kenneth. Now, besides that, the car registration number can change as well. For example, if I have a personalized number plate and I change my car, and I would like to retain my personalized number plate, and I can transfer that number plate to that car registration number to my new car. And whoever buys my old car from me, unless it is scrapped, I can apply for a new car registration number. So the car registration number is not static, it can change. Right? Okay, Kenneth also mentioned that you could have the same car registration number in another country. Right? But let's say that we have our traffic management system for Malta, so we're not going to have foreign cars in here. But that would be another point, because we could, yes, if we have a worldwide or a system that is going to cover more than one country, then we could have problems with car registration number because that could lose its uniqueness. But in this case, even if we know that the car registration number is unique, there is no other car in our system that is going to have ABC 123. However, because that can change, it doesn't give us a good primary key. Because ABC 123 up to that point in time is going to refer to a Mazda, for example, right? But then from that point in time onwards, that car registration number is going to refer to a Ferrari. I'm not going to buy a Ferrari, but I can dream. Okay, what about the other attributes? Kenneth quite rightly mentioned that the chassis number is unique. Now, these 5 attributes here are not unique. You have 2 Fords here. We have 2 SUVs, 2 coupes. We have 2 red cars. John Smith has 2 cars. So this does not give us uniqueness, but that should be, right, our primary key. Okay, so Kenneth is right there. We use as a number that should give us a very good primary key, right? Because it gives us uniqueness, it is not null, and it doesn't change. Now these are some concepts when we talk about keys. So the primary key is the attribute that uniquely identifies an occurrence or an instance of an entity. As we saw on the previous slide, as an example, this has a number. Now sometimes we need to use more than one attribute in order to identify uniqueness. And when we use more than one attribute to make up a primary key, we call it either a concatenated key, or a composite key, or a compound key. Okay, so these 3 terms mean the same thing: concatenated, composite, and compound. And this means that a primary key is made up of more than one attribute. We'll be doing an example of an ERD a bit later on, and we will be meeting a composite key. A candidate key is an attribute that could be used as a primary key. As Kenneth mentioned, we could use car registration number as a primary key. However, it is not that ideal, because although in perhaps 99% of the cases it does not change, in some cases, in 1% of the cases, it changes, and that will create chaos in our database. So that was a candidate key. It is a key that we considered. But then we chose another key as the primary key. Now it could be that that candidate key becomes an alternate key. It's a candidate key that has not been selected to be the primary key. So in the previous example, we had 2 candidate keys. We had the car registration number and the chassis number. In the end, the chassis number ended up as the primary key, the car registration number ended up as an alternate key. Now, another example of an alternate key or a candidate key in telecommunications, in telephony, we identify customers as through their account number. However, when a customer calls call center, there is no point in the call center clerk telling that customer, what is your account number, please? Because he or she will probably be answered with a swear word. Because customers don't remember their telephone account number. When you receive a bill, when you receive your telephone bill, the last thing on your mind is to look at the account number. However, the customer who is calling, the call center clerk asks him, what is your telephone number, please? The customer says it's 21123456. Then we can search the database on that alternate key. It is easier for customers to remember their telephone number than to remember their account number. So in a database, we allow alternate searches. Now that telephone number could have belonged to someone else 3 years ago. So when the clerk is going to search on that number using that number, she will probably get 2 or 3 records. But then obviously, the current one will be highlighted and she'll know which is the correct customer. Now the other term that we have is a foreign key. A foreign key is an attribute at the other end of an entity relationship from a primary key. The foreign key and the primary key are the glue that bind tables together. Right? And this is the way that we create our relationships. Now, when we talk about a relationship, between objects. We name what that relationship is. Now, a relationship is a long-lasting and persistent interdependency between entities. For example, we have an owner and a car. That is a long-lasting interdependency. It's a persistent interdependency. An owner owns a car. Right? So this is how we connect data objects to one another. When we talk about relationships, we meet two terms, cardinality and modality. Now, cardinality is the number of occurrences of one object that can be related to the number of occurrences of another. Here we go. Right, in the previous slide there. The number of occurrences, an owner. Can an owner have more than one car? Yes. Right, so, right. If we work on the concept that a car can't be transferred to another owner, that gives us a one-to-many relationship. An owner can have many cars. Can a car belong to more than one owner? Not at the same time. Right, so depends on the type of database that we are building. However, if we are taking into consideration that cars can change hands, then an owner can have many cars, yes, during its lifetime. So that gives us a many-to-many relationship. We are looking here, one-to-many and many-to-many. Now, a one-to-one relationship. Let's say that I am employed by a company and we have our garage beneath St. Martin's Institute. Wishful thinking and dreaming. Right? And every lecturer and every student has a parking slot allocated in the car park. But you only have one parking slot allocated. You can't come to school in two cars. Right? Now that would be a one-to-one relationship. You always come and park in that particular slot. Whatever car you come in. That slot is yours. So the relationship between you and the parking slot is a one-to-one relationship. Now let's talk about modality. Modality shows us whether the relationship is mandatory or not, or optional. In the one-to-one relationship that I mentioned, right, where every student and every lecturer will have a parking slot in St. Martin's car park, that relationship is optional because we could have students who don't have a car. So they don't need a parking slot. The other way around, you can't have a parking slot. Okay, yes. Theoretically, yes. Or practically, yes. We could have a parking slot that is not allocated to anybody. Because we will have free parking slots. Right? For further expansion, for example, or for guests. So a parking slot might not necessarily be linked to a person. Right, so that is modality. Now, how do we show cardinality and modality? So if we look at this diagram here, we have two data objects. We have a car and a repair action. Now, what is a repair action? A repair action is a docket that we raise if that car comes in for repairs. Now, if you look at the symbols next to the data objects, the symbols, the two symbols closest to the data object, so it is that one there, oopsie, and this less than symbol here, right? The two symbols closest to the data object show us the cardinality. And this means that the relationship is one to many. A car can have many repair actions. If the car has been in more than one accident and it has been brought to our garage more than once to be repaired, then every time that car is brought in to be repaired, we need to raise a docket. Right? So a car can have many repair actions. A particular repair action can only relate to one car. Right? Even if two cars collide and they are brought to our garage for repair, we are going to have a repair action for each car. Okay, because probably we need to send the bill to different people. Right? So that is a one-to-many relationship. Now, the two symbols away from the data object are the modality. Here we have a 1 and a 0. 0 means it is optional. A car may have no repair actions. It's a careful driver, or he bought the car and he just drives it on a Sunday. The rest of the week it is garaged. He's never been involved in an accident. Good driver, perhaps. And so it has never had a repair action. Or he has crashed several times but never brought it to our garage for repair, but has taken it to someone else. So we don't know about it. Okay, so this is modality, this is optional. A car doesn't need to have a repair action necessarily, مش بالفورس. It might have repair actions, but it might not have. But a repair action has to have a car linked to it. We can't have a repair action without a car in thin air flying around. Who are we going to charge for the work? Who are going to charge for the spares used? Right? Okay with cardinality and modality? Do I need to repeat or has it sunk in already?
Alright.
It's clear. It's very clear for me.
Okay, everybody okay with me?
Yep.
Okay, didn't hear any no's, so I assume that you are all with me. Now, what is the notation that we use for entity relationship diagrams? We use a rectangle to denote data objects, and we link them together with a label line to show the relationship. Now, normally, if the relationship is logical, right, if it is easily understood by looking at the entity relationship diagram, we do not label the line, we just place a line between the two data objects. In some variations of the ERD, we have a diamond, right, in the middle of the connecting line, and the label is within the diamond. I'm not particularly keen on this because especially if there are a lot of data objects on the entity relationship diagram, having a diamond with each relationship is going to clutter up the diagram. So I'm not really very keen on this. Relationships use special symbols that indicate cardinality and modality. It's the special symbols that we have seen on the previous slide. Attributes are represented by ovals or listed in the entity rectangle. We shall see on the next slide. Right, these two ways of representing attributes. Now, an important note here, if you are given attributes in an exam paper, you have to show them on the ERD. Right? Do not just show the entities, just the data objects. You have to show the attributes as well. Now, here we have a simple ERD with the diamond and the relationship name in the middle. So a manufacturer manufactures many cars. A car is manufactured by just one manufacturer. A manufacturer needs to have manufactured at least a car to be a manufacturer. So the modality is mandatory both sides. The car needs to have a manufacturer. We can't have a car being created out of thin air. And as I said, I'm not particularly keen on this diamond here, and ignore the shading at the back. Now these are how we show attributes, either as ovals linked to the rectangle with the entity name. Again, I don't like this a lot because here we only have an example with 3 attributes. But if you have 4 or 5 data objects, each with about 8 or 10 attributes, your diagram is going to look like a hedgehog or a pincushion. So again, it is going to be a bit difficult to understand. And the other way, my preferred way of showing the attribute is to list them in the rectangle itself. So here we have the entity name, seller, the data object, and these are the data items linked to seller. Now, you notice this is underlined and this is in red and underlined. Now, these denote the primary keys. So we identify the seller through the seller number. We identify an employee through the social security number. Okay, those are primary keys. Now, how do we draw an entity relationship diagram? And I'm going to go through an example because I think it's the simplest way for you to get to grips on how to draw an entity relationship diagram. This is going to be, an examination question on an ARD, so try to follow this with attention. If you have any problems, just let me know and I will repeat. And then there are some exercises on Moodle that you can try out and you can send to me for me to correct and to comment on them. And hopefully in our revision session, we can at least draw one or two entity relationship diagrams. Now, how do we come up with an entity relationship diagram? So first of all, we identify the entities. What is the entity name and what are its attributes? Now, entities normally read the scenario and the entities will be the nouns in the scenario. But be careful, not all the nouns will be entities because again, attributes are nouns. Right? So you have to distinguish between an attribute, something that is describing a data object. Then we identify the relationship between them. And after identifying the relationship, we identify the cardinality and the modality. How many of this relate to how many of this is the relationship optional or mandatory? And we draw the entity relationship diagram. Now let's go through an example. Right, this is our scenario. Bob's Paint Factory manufactures paints in different colors and in different sized containers. Its products are sold to ironmongers who send in their orders every Monday for delivery during the week. You are requested to identify the entities, identify the relationships, build the first cut ERD, and enhance the ERD with relationship cardinality. Now, I'll explain the difference between first cut ERD and second cut ERD as we go along. Right, so for the time being, just build an ERD and enhance it with relationship cardinality. So the first thing that you need to do is to identify the entities. So what entities do we need to model in this system here, in a sales ordering system? Think about it. Read it. What are the nouns there? Which nouns point to
Size.
data objects, to entities? How many entities can you identify there?
So the customers.
Customers, yes. Good. That's one entity. Which are the ironmongers? The ironmongers are customers, yes. Good, Floyd.
Products, I guess.
Products, yes.
And us. Oh, I was in the. It's in the paint factory.
But the paint factory was not model. That was basically building the system for the paint factory. So that is not a data object that we need to model. But there's another data object that we need to model there. The products and the customers, yes. Yes, Kenneth?
We have the orders.
The orders, yes. Okay. Now there are other nouns in there, right? Sometimes the students tell me colors and sizes. What do you think those are? Are they data objects?
They would be the attributes. No?
They would be the attributes, yes, very good. Okay, they would be the attributes. So we have identified the three entities: customer, order, and stock. Products, Floyd said products, I have listed them as stock there. Now, how do I identify the relationship between them? We build a relationship matrix. Now, on your PDF, this is all bunched together, overprinted. Okay, but on Moodle, there is an extract of this that gives a step-by-step build of the relationship matrix, what I'm going to go through now. So how do we build the relationship matrix? First of all, we list the entities vertically. Right? So we list customer, order, and stock vertically. Secondly, we list the entities horizontally but in reverse order. Okay, so we start off with stock at the top, order, and customer. The important thing is to keep the order. Now, it's not bad to do customer, order, and stock. Okay? But the important thing is to keep the sequence. I prefer to switch them around, right? And you'll get to know why in a minute. The third step is to blank off intersecting cells that have the same entity in both axes. Customer and customer. Customer is not going to have a relationship with himself. Order and order. An order does not have a relationship with another order. Stock item and stock item. They don't have a relationship between them, so we blank them off. We don't need to bother about relationships in these three cells here. Right? Another step is to blank off intersecting cells that duplicate an existing relationship pair. If you look at this, we have customer and stock. Here we have stock and customer, which basically is the same thing. Okay? We have order and customer. We have customer and order, which again is the same thing. Similarly with order and stock and order. So we blank them off. And we are left with just those three permutations of relationships. They are not all relationships because we look at what we call direct relationships. So it doesn't mean that we have to have a relationship in all three cases here. But the build up here is so that we eliminate a lot of these boxes here. We don't need to think about them. Now, if we had used customer or the stock, we would have had the shading the other way around. We would have had these three white boxes here in purple, and we would have had these three boxes here in white. The same thing. Right? But I prefer to have the top part to play around with. The next step is to tick off logical relationship pairs. Now, those pairs where there is a logical relationship. Does customer have a direct relationship with stock? It has to be a direct relationship. This might be a bit confusing at first, right? But it's important that you look for direct and indirect relationships because we only deal with the direct relationships. Are customer and stock directly related or through something else?
No, through something else, through the order, technically.
Through the order, yes. That's good, Floyd. Right, so customer and stock, there is no direct relationship. However, there is a direct relationship between customer and order. And what is the cardinality of that relationship? Can a customer have more than one order?
Yes.
Hopefully. Right? If our customers only order once from us, we're going to be in trouble. Can a particular order be ordered by more than one customer?
Yes.
Order number 1, 2, 3, for example.
Yes.
No, it's technically unique to each order.
Because it needs to be paid by the customer who ordered it. Okay, so, oops, okay, I gave my hand away there. So customer and order is a one-to-many relationship. Now, is there a direct relationship between order and stock?
Yes.
Yes,
Yes,
because
yes.
order is for stock. Now, can an order have more than one stock item on it?
Yes.
Yes. Again, hopefully our customers will order multiple items with the same order, not just one type of paint, right? But many different sizes and many different colors. Can a particular stock item, red paint in 5-liter cans, for example, be on more than one order?
Yes.
Hopefully, yes.
Hopefully, yes, again, because we'll be selling a lot more. So here we have a many-to-many relationship. So our customer and order relationship is one-to-many. Here we have a many-to-many relationship. Now, remember when I was talking about hierarchical network and relational databases? We said network databases, right, can model members that belong to different sets. Now here we have a many-to-many relationship, and with a relational database, a many-to-many relationship is impossible to show, impossible to set up. All right? But I will show you how we resolve that. For the time being, let's just bear in mind that it's a many-to-many relationship. Now, we have built our relationship metrics, and the next step is to build our entity relationship diagram. So this is our first cut TRD. We have customer related to order, order related to stock. Now, we need to show cardinality and modality. Right? So, one customer can have many orders, an order can only be paid by one customer. An order can have many stock items, a stock item can be on many orders. Now, if we look at modality, modality sometimes is very subjective. Here we have a customer might not have orders. Certain companies record a customer when they receive the first order. So the modality here would be mandatory. In this case, let's say that we have identified a new ironmonger who's going to open soon. And we've got all his details and we recorded him as a customer. However, when we sent a salesman to him to try to get him to order our products, he said, no, I'm very sorry, I'm not going to order paint from your factory because my cousin has a paint factory as well and I'm going to sell just his paints. So that customer might not have an order. Right? So the modality there is optional. An order has to have a customer. Someone has to pay for that order. We can't have optionality there. It has to be mandatory. Looking at the mandatory between order and stock, an order has to have at least one stock item. Otherwise, it's not an order. If a customer hasn't ordered at least one type of paint, what order is that? Now, and this is stretching it a bit, that is why I said this is subjective. We could have a particular stock item, purple paint in 50-gallon drums, for example, that nobody wants. We thought that the market for it, and we produce these 50-gallon drums with purple paint, but it has never been ordered. Right? So that is why I set it up as optional there. As I said, it is very far-fetched. Okay? But again, in an examination scenario, the modality, because it is subjective, you will not be penalized unless it is something that is logical like this. An order has to have a customer, so it is mandatory. But in certain cases, you can do them as mandatory or as optional. Now look at this note here. This is a many-to-many relationship that is impossible to implement in a relational database. So what happens? Are we stuck? No, because we use a technique that will resolve this many-to-many relationship. Now remember the term first cut TRD? Now this is the first cut TRD because we are going to update this ERD, we are going to enhance this ERD in order to eliminate this problem that we have here. So we are going to create what we call a second cut ERD, version 2. Now how do we resolve this? We resolve this by adding another entity, another data object. And we call it an associative entity. When we use an associative entity to resolve a many-to-many relationship, and we place it between two entities that have a many-to-many relationship. It can only exist between two entities. Here we have a customer that is not between entities. The order is between two entities, but customer and stock are not between entities. An associative entity has to have an entity on each side. Now, to complicate it a bit more, we also call associative entities composite entities or intersection entities or gerunds. We optionally denote them by having cutoffs in the corners of the rectangle. But again, it is not, you leave those cutoffs out, it is not a mortal sin. The associative entities also become database tables, right? Like the base entities that we started off with. So if we had to put the order line between order and stock, we'll end up with this diagram here. And you will note that the entities that had the many relationship pointing at them now have a one relationship. And the many relationships are transferred to the associative entity. So an order may have many order lines, but an order line can only be linked to one order. An order line can have only one stock item, but one stock item can be on many order lines because these order lines could be on different orders. Okay, so you see how we have resolved the the many-to-many relationship by creating two one-to-many relationships. Remember that the many always goes towards the new entity. Now here I haven't denoted modality. All right, modality can be 1 and 0 here, 1 and 1 there, like they were in the previous slide. So the full ERD, the final result, will be something like this: customer, order line, stock. Did you all follow that? Do I need to repeat part of it for someone?
From my end, I followed this, as in I understand how the order line, for example, is needed to
complete, to resolve
to resolve the issue of many-to-many relationships. But
yes.
I don't understand how the order line came into play here. Like, how did we come up with order line? As in
with the name order line?
Yeah, and as an object itself, as an entity itself, how did it come into play?
We had to come up with it because we needed to come up with it because we had a many-to-many relationship. Now, if you try to visualize an order, okay? At the top of the order, you have the order date, the order number, the customer who's placing the order, a delivery date probably. So those are the common attributes of the order. Then you have a number of lines where we write the different products that we need to order. With me?
All right.
So those are order lines. And that is why I named this order line. Well, it's a logical name to give it. Sometimes, all right, you have to rack your brains to see what you're going to call it. All right, sometimes it's very difficult to come up with a good name for it. But in this